Welcome, boys and girls, to our lesson 3. This lesson 3, we are going to look at just a few examples on work stroke energy. Okay, you have a few questions here and there. You just keep them. Some of them you will understand as we go along. Of most importance is that we are entering into a region where a lot of calculation will be done. So this is just to make you recall what we did in our last lesson. I have an example here of gravitational potential energy. We talked of two major branches of mechanical energy that you will encounter, potential and kinetic energy. Now let us see what is this. Okay, sometimes you may wonder which formula do I use, but in our last lesson I did say that when energy is transferred, work is done. So here we are going to look at an example. You have a body on this level. This is a body of mass m, and we want to lift it upward, vertically upward, from position A to position B. Okay, from position A to position B, we are lifting this body vertically upward. Okay, so there will be energy change from level A to level B. Whenever there is energy change, whenever there is energy transfer, then we can talk of work done. Okay, we can talk of work done. So that is what I want us to see. Okay, work is done when an object is lifted through height h. Okay, so we can say work is done when object is lifted through height h. Okay, through height h. So the work done basically would be force times distance. Basically it would be force times distance. So I can say here work is equal to force times distance h. But this translates to, and put it in another language, gain in potential energy. We talk of gain in potential energy. So I can get work done from the fact that when energy is transferred, work is done. So to calculate work done in lifting this body mass m vertically upward from position A to position B, I can use the formula for potential energy. That is to say, potential energy is equal to mgh. So that is the first thing I'm reminding you. What is it? The key thing is when energy is transferred, there is work done. So I'm trying to remind you, you can also get the work done using the potential energy formula. Potential energy is equal to mgh. Let us look at another example, elastic potential energy. Let us look at elastic potential energy. Elastic potential energy. Okay, this is energy stored in spring when compressed or stretched. Okay, this is the energy stored in a spring when compressed or stretched. So when you compress that spring, it stores some energy. Okay, so that energy stored, we can use it to get work done. But basically, what is in your mind? This is what we talk about. That if this is a spring, okay, initially, okay, and then you compress it now. Okay, so this one is compressed. And this is the original spring, original shape. So when we compress a spring, it will store energy. And that is what we say elastic potential energy. The first I reminded you is about gravitational potential energy. Okay? So I want you to remember one thing, that when we extend a spring, okay, when you put some mass on a spring, for example, let me hold this. Suppose this is a spring. When I put mass hanging down here, it will stretch. The spring will stretch. If I can take you back, maybe in a different way, just somewhere I focus a bit down here now. Let me focus a bit down. Let me focus this camera a bit down, then I can have another drawing. I rub this so that we understand what I'm talking about. Okay, so we have, this is a spring. It has a pointer. So it has no mass. We start. It has no mass. Then we come A, B. So if we have that, then we can talk of this as the extension. So extension E due to mass M. That mass, since it is pulling, we can talk of force W. Force, the force exerted on the spring is equal to W. So we can have force exerted on spring is equal to W, which is equal to mg. Okay? There is force you have applied, the spring has stretched. We can talk of extension when we compare the new shape and the original shape. The original shape and the new shape. So the difference in their lengths gives us extension. So as force increases, extension will also increase. Now let us focus down here again. You see another way of getting this. We focus down there. So for example, we are talking of force is proportional to extension. The graph is force in Newton, and this is extension. Let's say in meters. You have a linear graph. Okay, you have a linear graph. Okay, so if I am able to get this now, okay, this is F and this is extension E. This is F. Okay, so this is force plotted against extension. The gradient normally gives us spring constant. The gradient gives us spring constant. Okay, that is when we divide vertical quantity over horizontal quantity. Okay, but if I wanted to calculate the work done, so if I want work done on the spring, it will be force times distance. But we take average force is equal to 0 plus F over 2. 0 plus this force. It is the average force that we applied on the spring. Okay? The average force we applied on the spring. Okay? So, this gives us F over 2. Therefore, our work done will be F over 2 times distance, which is the extension which we have encountered, which gives us the formula a half F E. Okay? So look at this again. These are some of the aspects that you need to know. That work done is basically force times distance. So what we are saying here, the interpretation of force and distance matters with respect to the situation that you have been given. It depends on the context you have been given. It depends on the scenario that has been forwarded to you. So when we are dealing with spring, you can see some may argue it is a half base times height. A half base times height gives you the area. Area represents work done. Area represents work done, which is equal to half times base times height. This is a half, base is extension, and height is about F. So you can pick it from this, you can pick it from this. That is very important, and that is what we are going to pick it from. Remember that force is equal to KE. Okay, force is equal to KE. So this can come and replace something on that end. F is equal to KE. Okay, so work done is a half FE. You can remove F, and now it becomes a half KE squared. Okay, so I'll stop there, and then we will continue with lesson 4, where we shall still do more examples. We will continue with lesson 4 to do more examples. Please read this so that the lesson flows. If you skip one piece, you don't get the chain right. Till then, subscribe for more lessons. Bye-bye.